Oh, hello everyone. I'm Yufang Chen, and this is a joint work with Matthias Hasman, Ongzhua Leigang, Yong Li, Mingxian Cai, Angelia Tuwani, and Lijun Zhang. And this talk is about program termination analysis. First, why we are interested in this? Because it plays a critical role in software analysis. Total termination of a program depends on, total correctness depends on termination. I have a real-world example of this. So a few years back, I asked a student to write a sorting program and use a software verifier to check it as a homework. So he delivered this program. So at the end of the program, we add an assertion, assert sorted, and we give it to a checker to check whether this is correct. The assertion is never violated. However, this is not the right sorting program because the program can never leave the line L3. Basically, the value of I and j never change when they enter the loop, so there's no hope to get out. In order to make sure that the program is correct, we need to first make sure that it's terminated. And when it's terminated, the assertion is not violated. So that's why termination is important. However, this problem is undesirable due to halting problem. So modern termination analyzer gives three kinds of output: terminate, non-terminate, or unknown. And the research goal is to reduce the amount of unknown output from a set of benchmarks. So in this talk, I focus on a technique called automata-based termination analysis. This approach was proposed by Hasman et al. In CAF 14 and is implemented in a tool called Automata-Based. This tool won the Software Competition Verification 2018 termination category, and our optimization is used in this tool. How it works? So it begins from a sample program, and you sample a trace, and try to prove this trace is terminating using standard approach. And once it is proved, then it generalizes this proof to a set of traces with the same termination argument, and then remove this set of traces from the original program. This step is very expensive because it involves the so-called Buhi automata computation operation. The complexity of this operation is 2 to the power of n log n. So this is the main bottleneck of the approach. So our contribution is that we optimize this step. So after this is removed, then the approach just sample another trace and prove again, generalize and remove again until all traces in the program are covered. So that's automata-based termination analysis. So here I will use a more concrete example. So this is a sorting program. And to simplify presentation, I remove 2 lines that is not related to termination. So I create a control flow graph like this. So every state in the control flow graph corresponds to 1 line in the program. So L1 is L1, L2 is L2 there. And from L1, if I bigger than 0, then I can go to L2, which is the same to the program if you look at it. And from L2 to L3, I assign the value of j to 1. At L3, if j is smaller than I, then I go to the inner loop, the blue part. Otherwise, if it does not hold, j is bigger than or equals to I, then I go to the I'll go back to the outer loop. So now I hope you are convinced that these two are the same. So the approach first, the sample a trace from the control flow graph. In this case, I get the outer loop. So first, I bigger than 0, j assigned to 1, and repeatedly doing this outer loop. Outer means the j bigger than or equals to I, j minus minus, I bigger than 0, j assigned to 1. Repeatedly doing this, that's the meaning of the omega notation. I first use standard approach, or I did list a lot of reference here to prove that this trace is terminating. So typically the proof consists of a ranking function I, and you can see that this value I, every time when I enter the line L1, the value will be decreased. And if I want to leave from L1 to L2, then I has to be bigger than 0. So I cannot enter and leave I infinitely often. So this is a proof. And I generalize this to a set of traces for the same reason of termination. In this case, I get all possible traces that can visit L1 infinitely often. I will explain how to do this step later in detail. And after this, I get the first certified module, which consists of a Buhi automata whose language is just all traces that can visit L1 infinite often, in addition with the termination proof. I call this a certified module. So now all traces that can visit L1, I know they will infinite often, I know they will terminate. So I sample another trace. This trace only visits L1 once and then stay in the inner loop. Again, I prove it's terminating and then generalize it to a set of traces and get another certified module. The set of traces that visit outer loop infinite often. Now, we already proved the program is terminating because all traces in the original program belong to either P1 or P2. So any trace from the program P, I can show they are terminating, either use ranking function I or ranking function I minus J. So that's the automata-based approach for termination. So there's a missing part. I need to tell you how to generalize the proof for one trace to a set of traces. So here I use an example. Given this trace, automatic periodical trace, I bigger than 0, J assigned to 1, and repeatedly doing this inner loop. I first using standard approach to prove this trace is terminating. So the proof consists of a ranking function I minus J, and it must hold that this I minus J decreases every time when I visit L3. So the proof uses a fresh variable old rank to remember the previous value of a ranking function. Initially, it's infinite. And every time at L3, the old rank needs to be bigger than the current value of a ranking function. And every transition corresponds to a valid whole triple. Here, for example, for the transition from L1 to L2, this is the precondition, statement, and postcondition, and this corresponds to a valid whole triple, except that if you go out from L3, then you need to first update the value of O rank. If all is hold, then I can guarantee that the value of the ranking function decreases while visiting L3. It sounds like very complicated, but for this talk, you only need to remember two facts. First, almost every transition corresponds to a valid whole triple, and the accepting state has a special rule. This is sufficient to understand this talk. Okay, so now I can do the first step of generalization, how I generalize a trace to a set of traces. First, I can merge state with the same invariant. Why I can do this? Because after this, still every transition corresponds to a valid whole triple. Now I get a set of traces. I can actually do more. I can add actually all possible traces, all possible transitions, as long as they still correspond to a valid whole triple, then I can do this. So that's how I get the non-deterministic Buhi automata module, certified module. And so what's the problem of this thing? So because later I need to remove from the original program all traces that are already proved to terminate. This involves the Buhi automata complementation operation. And this is a very expensive procedure. If Buhi automata has n states, then the complementation may have 2 to the power of n log n states. So this is the goal of optimization. So we first proposed a multi-stage approach to do the generation instead of immediately go to non-deterministic Buhi automata, which has a very expensive complementation cost. I first try whether I can use deterministic automata to do this. If I cannot, then I try semi-deterministic automata. To complement a deterministic automata, a DBA, the cost is only linear. And to complement a semi-deterministic Buhi automata, basically this means the all runs becomes deterministic after touch the first accepting state. This is a spatial automata. The detail is not that important. The complementation cost is only exponential. So how I do this? So begin with an initial certified module. I obtain this after I merge state with the same invariant. I first do a modified subset construction. For example, in this case, from L1, I can go to L1 and L3 because the corresponding transition, the transition corresponds to a valid whole triple. I cannot go to L3 because the corresponding transition is not the valid whole triple. However, remember that the accepting state L3 has a special rule in the termination proof, so I cannot mix it with non-accepting state. So our choice is that, okay, we just remove all non-accepting state from a Markov state. If they have also accepting and non-accepting state, I just remove all non-accepting ones. So following this procedure, I can get the deterministic Buchi automata. However, there is no guarantee that our original word is included in the DBA certified module we constructed. If it is not included, we need to use more expressive module. So this we will try semi-deterministic Buchi automata. So it's actually very much the same. So we will still do subset construction. However, for the case that we have both accepting state and non-accepting state in the Markov state, now we don't remove all, instead of remove all non-accepting state, we partition them into two. So we have all non-accepting state in one Markov state and the accepting state in the other one, and we use non-deterministic transition to go to both of them. This is allowed because only non-deterministic transition occurs before accepting state. So this will give us a semi-deterministic Buchi automata. And in the experiment, we found that actually very rarely we need to use full non-deterministic automata. In our experiment, we found only 3 instances. So the main bottleneck now is semi-deterministic Buchi automata complementation. We find more than 1,000 instances. So this is the next goal to optimize the complementation algorithm for semi-deterministic Buchi automata. The current best algorithm for the complement semi-deterministic Buchi automata is called NCSB. And we have our idea of optimizing is that we try to delay non-deterministic transition in the algorithm. So we get the new algorithm called NCSB lazy. I will not explain the detail of this construction now. I only tell you that the properties we didn't really improve the worst case complexity, but our algorithm guaranteed to create no more state than the original one. Moreover, we have very impressive experimental result for this particular complementation algorithm. I will show you this. So we use 1,155 semi-deterministic Buchi automata generated from all different settings of termination analysis from the non-recursive programs in the SVCOM benchmark 2017. And in the scatter plot, you can see the number of states. So if a point fell in the bottom right part, then it means that our new algorithm, the daily version, is better. So if you focus on a point and look at the x and y axis, you can find that the number of states generated by the new algorithm is much smaller. But we don't have guarantee. We don't have theoretical guarantee instead of for number of transitions. So for some cases, we generate more transition than the original one. But in general, ours is still better. This also holds for execution time. So that's the second optimization. We optimize the SDVA complementation as well. At the end, we also, the third optimization is that we use on-the-fly algorithm to construct the complementation of Buchi automata. And we use a standard subsumption-based approach, also known as anti-chain-based approach, to avoid the creation of some unneeded state. So that's the third optimization we used. So that's the overall performance. So we implement all optimizations in the tool called Automizer. And we perform the experiment using all 1,375 non-recursive programs in the termination category of SVCOM 2017. And we have 3 settings: the single stage setting, which use only non-deterministic automata for generalize a trace to a set of traces. Multi-stage approach, we first try deterministic BA. If we cannot do it, then we try semi-deterministic one. If we cannot, then we go to non-deterministic one. And the multi-stage with optimization is multi-stage approach with also the better complementation algorithm and with the subsumption approach. You can see that the single stage approach, we have only around around 700 cases has unknown result. But when we use the multi-stage approach, the number is improved to almost only 300 unknown. And with the 2 additional optimization, the new better complementation algorithm and the subsumption approach, this number is improved to almost 250. So that's it. So we propose in the paper optimizations for automata-based termination analysis based on 3 optimization, multi-stage Boole automata generation, efficient complementation procedure for semi-deterministic Boole, and better state space pruning algorithm based on subsumption. They significantly improve the performance of automata-based termination analysis implemented in the Boole Automizer framework. So that's it.
Questions? I have a question. If you could roll back maybe 2 slides.
Yes. Sorry.
Roll back. Yeah.
Roll back.
Sorry.
This one.
Yes, that one. So is this limit of 300 seconds imposed by the competition, is this something in SVComp or?
Actually, this is shorter than the time allowed by SVComp. In SVComp, they use 900 seconds. But actually, the result will not differ too much if we extend it to 900. Because for the case that they can finish, then they can still finish. For the case that they are difficult, even if give you 3 hours, it cannot terminate.
I see. So if you can do it in 5 minutes, then all bets are off, essentially.
I think roughly this.
Okay. That's good to hear, yeah. Any other questions, concerns? No? Okay, let's thank the speaker once again, and this concludes the session.